Now it's recording. All right, so let's get started. This, only we have time. Let me give you these handouts over here. Doing with them today. All right, so take one of each. That's all. Let's get started. I got here new markers. I don't know if they're going to work or not, but so they might be too thick. They look a little bit thicker, but we'll make it work. So I got this stuff. Oh. I forgot my notepad, so I should be right back. All right, so you are working now on this project about the harmonic solution, about the free. Let's do a very quick review if you want. Can you take this page right here that we didn't use yesterday? So far we have dealt with the free, damp or undamped systems, which basically is a system where we have a block, a spring, and a damper. Okay? With a damping. So we have three cases. One, let's say, was repeatedly down, where basically we have the response that kind of goes to zero, no? After a certain time. The overdamp that basically is kind of similar. It looks something like this. Okay, sometimes it's hard to differentiate one to the other. And the third case is on the damp, but basically the response is still going to go to zero after a certain time, no? All right? So let me ask you something. I know this case is the more interesting one. But at the end of the day, do we know what's going to be the response after a certain amount of time? The solutions are going to converge to zero, no? Correct?
Yep.
So this case pretty quick, in this case as well, this one might take a little bit longer. All right? But after a certain amount of time, that means that the solution, the X solution we get for either one of those cases, so if you want, if we do this, the limit of the solution at x of t as t goes to infinity, what would that be?
Zero.
Zero, no? Okay? So I'm not saying this one is not useful, but we know the answer, no? After a certain amount of time. So the most interesting case will be if instead of the free vibration, the equivalent will be what is called, force damp vibrations. And okay, I did not bring the pages from the other day, but I think this should be 34. What is today, May 24th?
Yes.
Okay, May 24th. Today after class, I will try to scan all those pages, okay? And put them. Because the other student, which is taking the class with the video, told me that it will help to have one hard copy of this, as you might be watching the video, no?
Right.
I think that might be a good idea. So after this class, probably this afternoon, I will scan all these notes and put them on the same site as where you have the videos at the beginning. All right? So force down vibration. So what is force down vibration? So basically is the same as before. We have our block over here of mass M. We have our spring force over our spring over here, K, and we have our damper over here. Okay, and we assume no friction. So what is the biggest difference now is that this object, instead of displacing it and let it vibrate freely to the equilibrium position that is the stop, we're going to have a force in function of time, exciting that block. Okay? So we're going to follow the same procedure that we did for the free time vibration. The first thing we need to do is what? Find the equation of motion. So the first thing we do a figure or a sketch. Sketch, figure, diagram, whatever you want. So on that figure, we go here. So let's just look at the x direction. What we're going to have, we're going to have the spring force over here, the damping over here, and the force F of T over here. And in this case over here we have mx over dot. Alright, so step 2 basically is to write down the equation of motion using the Newton's equation, summation of forces equals to MA. And this will give us what? We'll have some on the x direction. Summation of forces equals to MA will be equal to what? Minus kx minus x dot plus f of t equal mx of a dot. Or at mx of a dot plus cx dot plus kx equal f of t. Okay, so let me ask you here a question. When we solve this problem, all right, so now let's say step 3. So, response, or to find the solution to this equation, what was the step we're doing first? What were we assuming?
Harmonic solution.
So the solution for x we say was equal to, what do you use, a constant?
Yeah, some constant times e to the,
Okay, of lambda t.
yeah.
Right? So in this case, I'm going to change it a bit. I'm going to use exponential notation. I'm going to say this would be I omega t. Okay? So assume solution. So let's say here, exponential notation. Now, what would be the easiest case to solve for f of t? So for example, f of t here is general, no?
Mm-hmm.
So can we assume also the force to be of an harmonic shape?
Yes.
That would be the easiest one. Now let's say you have a shaker, we also follow some type of sine function. So it will be x I sub naught I okay, so here I put omega t. All right, where let me specify something, I'll do that at the end. My teacher's confused, so we have those two assumed solution. Now that we have the two assumed solution, what can we do? We can go and substitute into the equation of motion, no?
Mm-hmm.
But before we do that, what would be x dot? X dot I omega
E to the I omega t.
E I omega t. And the x double dot equal to minus x naught omega squared E I omega t. Alright, so maybe I was going to do it later, but maybe let me do it here. What is omega over here? Is the frequency of the forcing force, I know it's redundant, but forcing force f of t. Okay, so basically let's say you can have f of t here to be what? We assume it's harmonic, so it could be some type of this function, no? And this one will have a certain frequency.
Mm-hmm.
Okay? What would have been the other choice? We could have assumed the solution to be in function of what frequency?
The natural frequency?
The natural frequency. But in general, what is going to be easier to be known? The frequency of the forcing or the natural frequency of the structure? I mean, let's say if you have a shaker, you can probably adjust the frequency of the shaker, no?
Mm-hmm.
So you will know what is the capital omega. It will be a lot faster, a lot harder for you to go and find out what is the natural frequency of the structure. You need to find the weight, you need to find the stiffness, which is not easy,
Mm-hmm.
okay? In order to find the solution for the natural frequency. So that's why here I selected the forcing frequency as the assumed one, because this one is always going to be easier to obtain. All right? But you could be assuming the omega n from this one, no? Yeah?
Mm-hmm.
Okay, should not matter. All right, so we substitute this over here on the equation. What do we get? Oh, this mark is a lot more, so 35. So substituting. Into mx double dot plus cx dot plus kx equal f of t. So this will become what? So we'll have, if you want, see if I can put them here. So we'll have m of x naught minus x sub naught omega squared ei omega squared plus c x naught I omega ei omega t plus k of x naught ei capital omega t, and this should be equal to f sub naught ei omega t. So over here, let me try to do something because this marker is going through. So to take a couple of pages, like this one and this one, and right on top of them. All right. So we have this. So what can we do on this side? We can factor by E I omega t, and then what are you going to get over here? Minus M x of naught omega squared. I should have factored by x of naught as well. Doesn't matter, we'll do it later. Plus C x naught I omega plus K x of naught will be equal to x of naught E I omega t. So why, now you can see why was it a good idea to use the same frequency for both of them, the response and the forcing function.
Because you can cancel out the exponential now?
So now we can cancel out the exponential on each side. Okay, and this will become what? Can factor out here again by x of naught of minus M omega squared plus C I omega plus K equal to x of naught. Okay, so if you remember, what are we trying to solve over here? Really? We're trying to find what would be the response x of t, no?
Mm-hmm.
So this one, if we know the frequency, we know what would be the shape of this. What do we need to know over here? What would be the value of the x of naught?
Mm-hmm.
Okay, so now we can come to this equation and solve for x of naught. That would be equal to what? S of 0 divided by M omega squared plus C I omega plus K. Okay? Or you can write this as x of naught equal to, you can do it this way, h of omega f sub naught, where h of omega would be equal to what?
1 over negative M omega squared plus Ci omega plus K.
Correct. We can just write this a little bit differently. This would be K minus M omega squared plus I C omega. Okay, so if you remember, what do we say was one of the consequences of having damping? what is damping producing between, let's say, the force F and the response X? What's going to happen because of the damping? Think about a car.
It's going to progressively lower the amplitude of the oscillation.
Correct? It's going to slowly reduce the amplitude, but the fact of having the damper is also going to create what? It's going to create a delay in
delay in the
you feeling
response.
whatever is, let's say, is the bump on the road. You don't feel it at the same time that it's happening on the road, no? The damper is creating a delay between the time of the bump and the time you feel the bump inside the car. Correct? So if you think about a sound wave, it's basically creating a difference in phase, no? Okay? So and here the difference in phase, you can see it where. This is a complex number. So if it is a complex number, this will mean that this is a phase. I mean, we go now into the problem, but so basically we could stop the solution over here, and if you do this, this will work. Okay? So now the only thing is that in most textbook we're gonna try to rewrite this in function of what? Of omega n and the damping ratio exit. Okay? So in order to do that, we need to go through some algebra. Let me take another page. Okay. All right, so let's go to here. After some algebra, and I think we're going to do it together. What do we have over here? We have the response x sub naught equals to f sub naught k minus m omega squared plus I c omega. Okay, I'm just recopying the expression from the previous page. All right, so using the fact that A plus IB times A minus IB will be equal to what?
A squared minus b, no, plus b squared.
A squared plus B squared, because you have this one, this AIB will cancel with this one, no? So we end up A squared plus minus I squared B, which would be B squared. So if we do the same thing, we multiply by the conjugate at the bottom and the top, what are we going to have? X sub naught will be equal to what?
F naught
F sub naught
times the quantity k minus m omega squared minus IC omega.
Okay, so you just write it down. Minus IC omega. Divided by what?
K minus m omega squared squared
Yep.
plus c squared omega squared.
C omega squared. Okay, so basically we could write this as what? X sub naught equal to, let's look at the constant term over here, F sub naught divided by K minus M omega squared plus C omega squared. And we keep here the complex number, K minus M omega squared minus IC omega. Okay, next, what do we know from complex algebra? If you have a complex number z bar a plus ib, okay, and let's say here we have z bar star, which would be what? The complex number, the complex conjugate, a minus ib.
Mm-hmm.
We know that we can rewrite this under which form? This would be the magnitude of the vector, so a squared plus b squared times e to the I fifth.
Mm-hmm.
Okay? And you could say this would be equal to z star bar e to the what? Minus I fifth. Okay? So in both cases here, z conjugate or the z normal, the magnitude will be equal to what? A squared plus b squared. Okay? And the angle phi will be equal to what? Tangent minus 1 of b over a. So this is the change in phase because of having a complex number that you're going to be introducing.
Mm-hmm.
So using this, let's rewrite this term over here. So the term k minus m lambda squared minus I c omega will be equal to what? K minus m lambda squared plus
Plus c omega squared,
c omega squared
all times e to the I phi.
e to the, but it should be the minus I phi, no? Because we have a minus over here.
Okay.
Minus I phi, where the phi would be equal to what?
The inverse tangent of c omega over k minus m omega squared.
Yeah, or minus c omega, no? It's negative.
Right, sorry.
Yeah, minus c omega divided by k minus m omega squared. So now we go and substitute this one over here. What do we get? X sub naught will be equals to, let's see if I don't put anything, so it would be F sub naught. Let's just do the top of K minus M omega square omega plus c omega square
Shouldn't there be a square root over that term?
That's what I'm just looking at. Yeah, because this is the magnitude, so I forgot here. So really, guys, you see this one is really a square root. So can I put here just 1/2? You see here, this is a square root, no?
Mm-hmm.
So this is 1/2, so we need here the 1/2. Divided by the same thing over here, k minus m lambda squared squared plus c omega squared squared e to the minus I Bye.